Our speaker today is Brigitte Servatius. She will be speaking on equilibrium stressability of multidimensional frameworks. Take it away, Brigitte.
Thank you, Sandra, and it's nice to give this talk. It's a new work, and Oleg Karpenkov was, I think, the initiator of this whole thing, so it's quite an international group. Oleg is now in England, Christian is in Austria, Gaiane in Russia, Herman, I don't know, and Dirk is in the Netherlands. So it was nice that we all could get together in Edinburgh, and we had a good time developing this. So that's, in some sense, the overview. I want to give the definitions, and probably half the time is spent on definitions, a quarter of the time on stressability, and an eighth on the exact forms, and a 16th on Cayley algebra, and 30 seconds left for lifts and stressability. So what's a tensegrity? And here's a picture that I know exactly how old it is. It is over a quarter of a century old, because this little peanut here is getting married next month and she's 26. But this is Bob Connolly and his wife and son, who is now also a Cornell professor. And we were standing under this needle tower, Snelson's needle tower. And what I want you to think about is that it looks impressive from the far, because you only see these bars that seem to float in the air, and the cables provide the tension that this is actually quite stable. We actually stood underneath there and played with it, sort of plucked it, played it like a musical instrument. But if you go there now, there is a big sign, do not touch. So maybe we were the guilty ones for this, but it's still standing in Washington, DC. And here's a little bit of history of tensegrities. Maxwell started it all out in 1864, and he has frameworks and phase loads, and it's quite sophisticated work, but mostly, a lot of matroids. Fuller was actually teaching Snelson. Snelson was a student of Fuller's back in the 40s. And Snelson created probably what's called the first tensegrity, but the word was coined by Buckminster Fuller sometime in the 60s. In 63, Tutt wrote this amazing paper about how to draw a graph. And he used essentially the same ideas. He bolted somehow one face into the plane, and then interpreted the edges as springs and said, well, this whole graph will draw itself by minimizing its energy. And Connolly and Whiteley pushed this to a very high level and talked about rigidity and energy and minimizing the energy on these systems. Then Whiteley and Lee in 96 had the first articles on stressed polytopes, and Rybnikov did a construction of multidimensional tensegrities. And all of this happened in the past millennium. And we got together in 2020 in Edinburgh, and you will hear what we did then. So here's a definition of a D framework. So D is an integer, and the D framework consists of a quadruple set of edges, a set of faces, a set of incidences, and normals. So the edges are a collection of D-1 dimensional planes in R capital D, and R capital D has nothing to do with a little d. It's just supposed to be bigger than this little d. And the faces are a collection of little d dimensional planes in R capital D. And the incidences are a subset of the ordered pairs, face-edge pairs or edge-face pairs. And here is sort of a schematic. You can, these gray little rectangles are just part of the planes that we are considering, and the black edges are parts of the edges that we are considering, and this is capital D is equal to 3. And observe though that the faces are not really rectangles, right? They are we want to consider this, the infinite planes in RD. So this is only drawing a little piece of the picture. And the normal vectors are given, they are just unit normal vectors for each edge face pair. You want to draw unit normal perpendicular to the edge contained in the face that the edge is incident in. So these little blue vectors here, ignore the red and the yellow. Those little blue vectors are supposed to be indicating the normals. So now we want to say what a stress on such a framework is. A stress is just a function that assigns a real number to each one of the faces. And a framework together with a stress is supposed to be is said to be in equilibrium for this particular stress. If for each edge you can sum over the faces that the edge is contained in, and the normals scaled by the stresses sum to 0 around this edge, then you talk about an equilibrium stress or a self-stress on this framework F. So such a framework is called a tensegrity if there exists a non-zero self-stress on it. And you all know the classical example of graphs in the plane. So there the capital D is equal to 2 and the little d is equal to 1. So the edges are actually what is called the faces and the vertices are called the edges. So this gets a little bit confusing, but you know what I mean. So I want to give you an example in the plane. So capital D is equal to 2, little d is equal to 1. So our edges are the vertices of this graph. And now we want to think of this as a tensegrity. So does there exist a non-zero self-stress on it? And you can think of these expanding spokes to be equilibrated by the contracting rim. So here I've drawn in the force vectors, the Maxwell kind, the Maxwell way. And what you see, if the red vectors indicate forces on the vertices, all the vertices are in equilibrium. So the vertices of this graph are actually the edges of my multidimensional framework. So this graph is in equilibrium. None of the vertices will move if the forces on the vertices are that way. That means the outside edges here are under compression and the inside edges are under tension. And the graph will not move, right? But the engineers are very much interested in what the forces are in the members, say, of a building. So they will perform such computations. And to get back to Snelson's needle tower, under which Connolly stood with me 25 years ago, this is the essential piece of it. So here you can again think of these blue things as expanding or under tension, or well, they are trying to expand, and this expansion is compensated by the tension in those red cables. And then so Snelson built his needle tower from this basic structure. So again, this is a tensegrity, but you see that capital D is now 3 and little d is still equal to 1. So my edges of my framework are the vertices, and the planes are the red and the blue edges. So now I want to give you an example of little d is equal to 2 and capital D equal to 3. And we want to just consider the cubes and I have to describe to you what the edges are, all the lines that are contained here. So you can think of just the edges of the cube and all the face diagonals. That's what I want the edges to be. But the faces are supposed to be all the ordinary faces of the cube, but think of them as extended planes in 3 space. And I also want the faces that contain pairs of opposite edges. So there are 6 planes of this, with 6 pairs of edges here. And then I want to consider the 8 planes of the dual tetrahedra that are within this cube. So there are quite a few. It's quite a large structure if you think of this object. And so it's just I have to tell you what the incidences are. I want the incidences to be the natural incidence denses that the edges have with the described planes. So what you can think of, that each edge here of the cube is actually incident with 3 of the faces. And also each diagonal of the cube is incident with 3 of these described faces, namely 2 which correspond to the dual tetrahedra and the 1 that corresponds to the slanted rectangle within the cube. So the fact that this face diagonal is part or incident with the front face does not count as an incidence because I haven't described it.
Contained it, not
so, okay, so now we can ask, is there a stress on this object? And I have to first also say what the normals are, but the normals are supposed to just go in the interior of these faces, because each big plane actually is bounded by 3 of the lines. So I can actually point all my normals into the interior. And if I do that, then it's sort of fairly easy to see that there is a self-stress on it. And the self-stresses on the 3 types of planes are in relation 1 negative square root of 2 square root of 3 over 4. And that's also quite easy to see. So what you think of is these faces made of some material. So if so the positive numbers you might think of are contracting, and the middle planes sort of, they are pushing out onto the edge. And if this happens, then what this edge here, for example, on the top feels is a little contraction from the top and the side face. And this contraction is compensated by this slanted rectangle pushing out. So in the end, if the self-stresses on the faces are in this ratio, the edges will remain in equilibrium and not feel anything. So now we want to say, this is not, for this particular example, it's sort of easy to see that there's a self-stress But what are criteria for rather complicated things in this setting? And what I want to define first is what a phase path and a phase cycle is. So it seems a complicated definition, but it actually is quite straightforward. So you want to look at the edges, and you want to look at a sequence of edges, which are now these d-1 dimensional planes in RD. And you have two sequences of phases. The one sequence is indexed sort of with the double indices, and the hatted sequence is just single indices. And what you want is that the edge EI is contained in Fi plus 1 and in Fi minus 1 and I, and also in the ith hatted phase. So the incidences then denote the set of pairs defined by these inclusions. And the picture will be quite clear. So n can be chosen arbitrarily, just normal to the edges contained in the phase that the edge is contained in. And so here's a schematic for the situation. And here the edges are indicated by just vertices and the faces by line segments. So each edge is actually contained in exactly 3 of the faces. And so a phase path of length 3 is in this left picture, and a phase cycle of length 5 is in the right picture. So here's our first stressability criterion, or first theorem, if you want. So such a generic phase-connected trivalent D framework. I should explain actually all these terms. Generic here just means that the phases are distinct, because we usually think of them as little pieces, but if you think of them as entire infinite phases in this R capital D, they might as well coincide, even if we look at them locally. So phase connected means there is a phase path from any given phase to any other given phase. And trivalent means that each edge is contained in exactly 3 phases. And for such a generic phase-connected trivalent D framework, the following statements are equivalent: that this framework has a non-zero self-stress. And in fact, if it has a non-zero self-stress, then that non-zero self-stress is actually non-zero at any one of the planes. And the second condition that is equivalent to the first, that for every 2 D planes, A, Fa and Fz, the stress transition does not depend on the choice of an induced phase path D framework. And I will explain a little later what the stress transition is. And every induced phase loop D framework on F is self-stressable. So let's see if we can understand that. So if we don't have a phase cycle, if we just have a phase path, right? Because we said trivalent D framework connected. So if we just look at a simple phase path, then this has a one-dimensional space of self-stresses. So this is quite easy to see because, well, at every edge you have 3 normal vectors. The planes are not identical. So these 3 normal vectors to the edge, they are living in a plane. And there is a dependence among them. So you can find a non-zero stress on the edges, and you go from, you define your stress to be non-zero on one of the faces and can compute the stress so that there is equilibrium on this first edge. And then you proceed, right? So then you can say that you can now calculate uniquely, given your first choice for stress on this first phase, you can continue your path to the last phase. And the stress is completely determined by the first non-zero choice that you made. And you get non-zero stresses everywhere. And all the stresses of all the planes are either simultaneously zero or simultaneously non-zero. So that's quite easy. So now we want a little bit of a technical detail. We want to orient the edges because it can get rather confusing. So if you have more cycles than just one cycle, right, then you want to somehow keep track of how the normals interact. And so given a phase path, just an ordinary phase path, we want to fix an orientation of just some single edge. And given an orientation of this edge, we want to set the orientation for the next edge on the phase path to be determined by the first choice. So we want to actually look at my first choice of edge here. And now the normal vector could be pointing in two possible directions, either inside or outside, right? And so we want to see how we should orient the next edge on the phase path. And that will depend also on the normal vector here, which could be either pointing inside or outside. And the way we are going to do this is we want to start out with a frame. So here we have the situation that we have chosen the orientation for our edge and the normal vector, so that we can think of this as a coordinate system or frame. And we want the orientation on the next edge to be such that these two frames differ by an orientation reversing automorphism. So that's quite clear. So if we look at the situation here, then we should orient the next edge up. If the normal vector on the next edge was actually pointing outward, then we should move our next edge down. And so if both were pointing outward, we have both of the edges pointing upward, and we can continue on the phase path to orient all the edges. So we call a phase cycle now orientable, edge orientable, if the edge orientation transition around the cycle returns to the starting edge in its initial orientation, and non-orientable otherwise. So what is indicated here is just a phase cycle. You look at it, you might look at it from the top. So the edges are actually just the vertices, but think of them, if they have a plus sign in this picture, then they are pointing upward, and if there are minus sign, the orientation is supposed to go downward. So certainly this phase cycle is orientable because the normals that are given, the red ones here, right? So if I start out and say this edge is pointing upward, this is pointing upward, so all the frames are actually mirror images of each other. if I start out with this particular situation, that my normal vectors are both pointing inward and outward, then I have the same situation, right? It's perfectly orientable. If I point, if I start out with this edge negatively oriented, then I can accommodate a negatively pointed one here, then go to plus, 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 and if I go all the way around, it matches. But if I start here, for example, and I have my edge pointing upward, then I point up and have to point this one down, next one down, next one should be up, but I have no chance of actually orienting this so that I get back to plus. So this cycle would be non-orientable. So we want to see what this edge orientability actually does for us, but the situation is actually quite simple if we reverse simultaneously all the normals at a single edge. Right, and remember, the normals were actually chosen arbitrarily. So the normals are given a priori, and we ask, how does the orientation of our edges affect any kind of computation or orientability? Then if we change all the normals at any edge, then orientability of any edge cycle is, or the self-stressability is not affected at all. And if we reverse simultaneously the normals that are going around the phase cycle of the doubly indexed phases, then nothing happens either. So self-stressability and orientability is not changed at all. And if we only reverse the normals of the hatted phases, then again, self-stressability and orientability doesn't change. So let's see if we can figure out the phase transition or the force transition for an orientable 3 cycle. This is sort of the easiest situation that you can think of. And so here is the situation. If I have a 3 cycle, that means I have a cycle of 3 blue phases, and they intersect in the black edges. And then the yellow edges are the F hats. And I have drawn in the normals that sort of don't look like unit normals because, of course, the faces are slanted. So they look distorted, but I tried to make this a 3D picture. So now what we want is to think of this as all the 3 edges sort of oriented upwards. So we have an orientable 3 cycle, and we want to figure out a stressability criterion under which it actually happens that there is a non-zero self-stress on this figure. So again, what you can do is start to say that, well, at every edge, those 3 unit normals are dependent. So I can, for example, figure out or say that my front face should be stressed, the front blue face with just stress 1, then I can uniquely determine the stresses on the 2 other little arrows. So that means on the back face and on the first yellow face, so that there is equilibrium at the first edge. If I want the same scaling factor for the second edge, right, then my stress on the back face and the second yellow face are determined. And as I come around back to my front face, the stresses ought to match. So there ought to be a condition. Now in this orientable case, the condition is fairly easy. All you have to make sure is that the yellow edges actually do intersect in a line. Right, so it's a straightforward geometric condition for this 3-cycle. But if my 3-cycle is non-orientable, then the situation is a little bit more difficult. So here's a geometric construction that constructs something, but I'd rather show you in the picture right away. So now I want you to concentrate on the picture, which is not 3D. I just drew that in 2D, and my edges are E1, E2, and E3. And I have non-orientable normals. So I have chosen the normals on the edge from E1 to E2 to point inward. So you can think of these as unit normal vectors. But on E2 and E3, I want them to one turn inward, one outward. And I want now a condition under which I can have equilibrium at each edge. Right? So if I start out with my E1 to be a unit vector, then I can compute the forces in F hat and along the edge from E1, along the phase from E1 to E3. And I can transition this stress to E2. And now I want the same scaling factor to be used for my edge E3. So I have, in case my F3 hat was pointing in this direction, and I want my third stress here to match with what I got from my first edge, then I can translate by this construction the situation into the previous condition by constructing this F3 hat bar. And I can say that F3 hat bar and F1 hat and F2 hat again have to meet in a D-1 dimensional plane. And see how this F3 hat bar is actually constructed just from the given ingredients. Right? So it's a geometric construction, and which then translates the condition under which there is a stress transition that gives me a non-zero stress on all the faces, which equilibrates on all the edges, is a geometric condition with F3 replaced by F3 hat bar. So this is summarized in the next theorem, or I've just shown the pictures, right? The similar pictures in the orientable situation, right? It's an immediate picture. And in the non-orientable case, when I want to resolve this F3 hat in this particular way, I construct my F3 hat bar and the pictures then become identical, and we can summarize this for this 3-cycle, that the dimension of the intersection of the 3 hat faces must be D-1, or the intersection of the hat faces with F3 hat replaced by F3 hat bar must be D-1. So that's our first stressability criterion. And of course, if you have longer cycles, cycles, you see that the phase transition then, or the force transition, or the stress transition, if you like, is of a similar nature. It's just a little bit tedious to describe in terms of geometry. And so we want to get to stressability via these multiplicative one forms. So I first, there's a little bit of more definitions. I don't particularly like the notion of dual graph, but I'd like to hear from this audience if I'm right or wrong. But what we want to replace, we want to draw a graph whose vertices are the d-dimensional planes of our framework, and the edges of this dual graph are connecting two of the faces if they share an edge, if the faces share an edge E. So far this corresponds to the dual graph, but on the other hand, I rather think of it as the line graph. But then, of course, that's hard to say because my lines are actually representing faces. But that's the general idea. So if you have a face which is now indicated in this low dimensional picture as an edge, and the edges are actually those vertices, this dual graph is actually not the dual graph, but it's the line graph, but not important. So I try to draw a 3D picture. Again, the faces are now indicated by those gray rectangles. The edges are the black lines. And this dual graph is the yellow structure. So what we want to get a hold of is we want to actually have a little bit of an orientation on the edges of the dual graph, but we are mostly interested in the edges that have actually endpoints that are of large degree. So these faces that that are not part of a phase cycle as faces with double indices. We are not so much interested in those. But if we want to actually go around in our dual graph around the cycle, then each edge of this dual graph is actually determined by a triple of consecutive edges. And so we can consider these edges actually as arcs going from EI minus 1, EI to EI plus 1. So that's how to get a direction on the edges of the dual graph. And now we want to say what an exact one form is. I actually want to get rid of this thing here.
You can just move it. It looks like you can't move it, but you can.
I can move it.
Yeah.
Somewhere.
Sorry.
Back, right? So we want, for any graph with directed edges, consider, so any digraph actually, consider, describe what a one form is. So now I've lost.
It's not, you have to. And then, yes,
Now again. Okay. So a function from the arcs of a digraph into the positive real numbers is called the discrete multiplicative one form. If the function on the reverse edge returns is the reciprocal of the function on the arcs. So if I go the other way around, right, I get 1 over the number. So one of these one forms is exact if for every cycle of directed edges, we have that the product of the arcs of the function is equal to 1. So now we consider one of our phase paths again, or well, just consider the dual graph, and we want to define this multiplicative one form by this affine ratio, which is actually quite easy. I mean, it looks a little bit complicated, but the situation here is just easy. And that was the pictures drawn in here. So every edge is part of three faces. And the faces that have the two indices, there you go along this phase path or phase cycle, and the hat face is just attached. Here, the normals are given in blue, and the normals are in one plane, so they are just unit normal vectors. And if I have three faces meet at this edge, and I want them to be in equilibrium, I can certainly find coefficients that equilibrate, or that gives me vector sum 0 because they are dependent. And this Ri is actually, this vector is computed to be the intersection of the two tips of the normal vectors with the line on which the third normal vector lives. And of course, that's now living on a line. And this affine ratio is nothing else but the, but the ratio of the linear dependence coefficients between the three normal vectors meeting at this edge. And coincidentally, this is nothing else than the stresses of consecutive edges along this phase. So if I want, the stress transition has actually this nice interpretation in relation with the unit normals. So that's not surprising, but it gives us a nice criterion now in terms of multiplicative one forms. So we can now say that the generic trivalent D framework is self-stressable if and only if the above discrete multiplicative one form for the dual graph is exact. So our dual graph can be quite complicated and have lots of cycles. And that's why we need, for example, the edge orientation, right? Because on all these cycles, the stress transition will be actually complicated to compute. But once we define this multiplicative one form, this might be an easier criterion to actually computational. It's easier than the previous. Now we want to get to the Cayley algebra conditions. And in some sense, you have already seen them. So we have, if you're not familiar with Cayley algebra, this is just a very rough and quick description of it. The operation of wedge is the span of two planes of whatever dimension you have. And the operation of join is the intersection of P and Q. And so you have seen this already, right? So for the phase cycle D framework, we have this edge orientability in the case of a 3 cycle, namely the dimensions of the hat faces must intersect in a d-dimensional plane. So in terms of Cayley algebra, this is just the intersection replaced by the hat. And for the non-orientable case, we replace F3 hat by F3 hat prime. And this F3 hat prime was actually computed already using Cayley algebra. So in Cayley algebra conditions, we can either say the dimension of this 3 hat is d-1, or we can give all these conditions defining how our F3 hat was actually computed. So this is just in terms of Cayley algebra. Why we want to do that? We want to now just take any cycle that can be as long as we want to have it. So it can be the phase path or phase cycle. And we want to reduce to the case of a 3 cycle. So I don't even want to go in detail for this through this definition, but I want to just show you the picture. So we started, this is only a path, a small part of a phase cycle or phase path. And what we want to do is we want to make it shorter. So what is indicated here is that I'm, in a sense, intersecting the green and the pink phase. And I want to insert a normal here, but and I want to delete these other 2 F hat phases. And of course, it depends on the direction of this phase. This 3rd phase that I insert will depend on the directions of the phases via this Cayley algebra. But this is a well-defined operation. What is important is that the stress transition is actually legal. So if I start out with a stressable framework, then the stresses on this will be determined just the same way. So it will be stressable or non-stressable, and the stressability will not be affected by the surgery. So what is the point here? So if you believe that, so I'm skipping the details. So we want to think of F be a trivalent resolvable D framework, and let the C1 to Cn be all pairwise non-phase homotopic phase loop D frameworks. So I want to just look at all the loops that, or phase cycles that there are. Then F has a self-stress if and only if it fulfills the Cayley algebra geometric conditions for the cycles C1 to Cn obtained by iterative application of this surgery. And all we have to check then after the surgery is if the Cayley algebra condition for the 3 cycles is met. So this makes life simple, right? Because we say we can do this surgery on all the longer cycles, make them 3 cycles. So in some sense, this corresponds to triangulating the planar graphs, if you like, right? But all then you have to check is the condition on the 3 cycles. So I want to only indicate one little thing about this condition. I want to say that Rybnikov in '99 actually extended a lot of this algebraic geometry of stressable manifolds to all dimensions. So he starts out with just a d-dimensional manifold, and these chambers actually consider the skeletons of all dimensions. And the important part here is that liftability implies self-stressability. So that's already what Maxwell has observed a long time ago, that anything stressable sort of comes from a dimension higher. And just think of the example that I started out with, the tetrahedron in 2D. right? It's liftable into a tetrahedron in 3 space. We are thinking of that, right? But no matter how you project it, the projection actually gives you a stress, a resolvable stress on the edges. So this carries through. And so in some sense, this is part of what we want to consider, that the liftability gives you a collection of nice examples of self-stressable d-dimensional frameworks. So with that, I just want to say thank you. And I have a few minutes for questions, if you have any.
Thank you. Let's thank the speaker.
Oh, thank you. Great talk. Thanks. That's really cool.
So I'd like to mention a couple of things. One is that Seth suggested path graph instead of dual graph.
Path graphs.
I suggested face graph.
Face graph, excuse me.
Yeah.
Thank you.
Face graph. No, thank
I
you.
had
That,
one letter correct. The A. Sorry, Seth. Okay. Face graph, yes.
face graph. Thank you. That is a great suggestion.
And I was wondering, what paper of which Ribnikov is this, and what paper is that?
So Rybnikov, that is
Should be on the
actually,
first slide.
so, but I didn't actually put in the,
Can you just
The
tell me the name of the
citation.
paper or something like that?
so it's Konstantin Rybnikov, and he's actually at UMass Lowell.
Yeah,
And
I know him.
so I can, yeah,
Yeah,
so I should,
I'm sorry, please go ahead.
so it's an older paper, but it's a long paper.
Yeah.
And I don't know, we should look up the citation, but I don't have the paper open.
Okay. It's okay, Brigitte. I can look that up with that information.
Okay.
Now,
Yeah.
have you considered, that might be the one that had a mistake, which led to 2 papers that we wrote together about gain graphs and the application of gain graphs to structures like what you have, although I don't remember anything of the details. But here's why I'm bringing this up. It seems to me that you have implicitly some signed graphs or bidirected graphs and also some gain graphs. For instance, the discrete multiplicative one form is just a gain function on on the face graph, we might call it, and exact is just what's known as balance. And this is easy to determine by simple computation on the graph. Have you thought about this connection at all? I don't know if this ever occurred to you.
No, I have not. So
Well,
I'm
yeah,
grateful.
it should
This
be
is great.
mentioned, you take logs.
Logs? No,
No.
Seth. You use multiplication.
Mhm.
You don't need logs.
So I don't need one.
Logarithms.
Okay.
You went
Oh,
with
no,
Not
I'm
too
sorry, yeah.
But gains are usually additive.
Mhm.
No, that is wrong. That is not a true statement. Who said that? Peter, was that you?
Not me.
No, who said that? It's not true. Gains can be additive or multiplicative. It doesn't matter.
Okay.
Oh, I see. Well, I may be not aware of those.
Yeah, I think when additivity is stressed, they're called voltage graphs.
No, that's not true, Seth.
No?
I'm sorry. You're just completely mistaken about this. Voltage graphs are another name for gain graphs. And the reason I'm not calling them voltage graphs is that people get confused with Kirchhoff's voltage laws, which voltage graphs do not satisfy.
Mhm.
And the reason they were called voltage graphs in the first place is because there was something called current graphs, and these were dual to them. And current graphs did not satisfy Kirchhoff's current laws.